It should be
Okay,
recording right now. Thank you.
great. Thank you, everyone. Welcome to this last Create seminar of the year. I'm very excited to introduce today not one, but two speakers. Well, we have Professor Samida Maharjan, who is a full professor at the Department of Informatics at the University of Oslo in Norway. Professor Maharjan received her PhD in distributed systems and networks from the University of Oslo in 2013. She also worked as a research engineer at the Institute for Infocom Research in Singapore, and she was a visiting scholar at the Zhejiang University in China and at the University of Illinois at Urbana-Champaign in 2012. And her research is on, well, energy efficiency, as all of our invited speakers in this series, with a focus on vehicular networks, 5G and 6G, network security, Internet of Things, and AI for networks. So in addition to Professor Maharjan, we are also joined by Dr. Xiliang Zhang, who is a postdoctoral researcher also at the Department of Informatics at the University of Oslo, working together with Sabita. So his interests include energy informatics, privacy, preservation, machine learning, and stochastic systems. And he was previously a postdoc at Chalmers University, also working on privacy preserving machine learning. So without further ado, I would give the floor to you. If you can please share your screen and take it away.
Yes, sure. Let me share my screen. Do you see full screen?
Yes, right now, yes.
Yes. Okay. Yes. Let me start my timer. That's necessary to keep me in track. Yes. Good afternoon and good morning there, everyone. Thank you, Nimet and Oana, for the invitation. Also, Arno, actually, Arno approached me first. Thank you very much for the invitation, and also thank you for a nice introduction. I am a professor at the Department of Informatics, University of Oslo, and today I will be presenting about this over here. Yes, about a participatory approach and an integrated perspective towards sustainable energy transition. Yes, this is the Energy Informatics Group at EFI, the Department of Informatics at UIO. It's a part of the bigger group called ND, Networks and Distributed Systems. We have one postdoctoral researcher, Shi Liang, who will also be presenting a bit about his work towards the end of the presentation today. And we have 5, 6 PhD students and master students. My research activities, it's on a couple of different things, but I like to put it within this umbrella of interaction modeling between different agents, different stakeholders for resource optimization, resource of different kinds in different domains. I have worked extensively in smart and sustainable energy systems, including electric mobility, but also in networks. So these are different domains, 5G, 5G beyond, 6G, with a special focus on vehicular networks and mobile edge computing. More recently, I wouldn't say shifted, but I have been trying to extend my research activities in the area of data privacy and cybersecurity, which is a little bit beyond the conventional cyber physical security notions. It's more towards the notion of trust and trustworthy systems, and more end user oriented. The outline of today's talk. First, I will introduce the big picture, energy efficiency and sustainability. Then I will introduce the cross-disciplinary project called PRETEM, Privacy Preserving Transactive Energy Management, which I am leading. And then I will present a few papers, 3, 4 papers on participatory approach and an integrated perspective, which are the publications from this project. Energy efficiency and sustainability will constitute an overarching theme for many current, emerging, and future applications, including smart grid, electric mobility, networks, autonomous driving, 5G, 5G beyond, 6G, to name a few. And another very interesting one here, artificial intelligence, which is now quite ubiquitous, quite prevalent across all domains to improve the performance in different ways. And when we talk about AI, by now we all understand that this is AI models can be quite massive energy hungry, especially deep neural networks, and nowadays the large language models. In this picture, it's basically an illustration of how to gain an accuracy of about 10% from 69 to 79, 80%, you may need to go from 500 million parameters all the way to 8.5 billion parameters, which is how many folds? 18 times, 19 times more. And in terms of energy consumption and carbon emissions, it's a lot. To give to put this in context, in 2019, the transformer network which was trained on with 213 million parameters that consumed about this much electricity, 626 megawatt hour. That is about the emissions of 5 cars in their lifetimes in the US. So this is just to put in the context of emissions, carbon emissions. These numbers might be slightly older, so there might be some new changes. But even if we look at newer figures, they are probably not exactly the same or not exactly proportional, but we know that the energy consumption is quite massive. And I also read a recent paper from last year where it says that whatever energy is consumed for training, that's of course very high, but the way LLMs are being used for almost everything now, they consume much more energy for the use, which is also something that can be very interesting to the people like us who are working on sustainable systems and sustainable energy transition. So is it only talking about challenges and bad news and energy consumption, which seems to be the starting point of discussion, at least in this kind of community? But it's not all just concerns and challenges. Of course, there are many challenges to solve, but there are also good things that are happening. So these figures and the numbers here are from Google's Environmental Report 2025, which tells us that data center energy consumption and carbon emissions have reduced by 12%, despite the growing demands. So if you look at this figure on top here, you see that the energy consumption is basically growing, the blue bars, but then carbon emissions we're also more or less proportionally growing, maybe not exactly linearly, but you see that there is some saturation here and here, and it starts decreasing now. This does not mean that we have achieved or we are very close to achieving all our goals, but it just means that there are some positive developments as well. And of course, this is not just one particular approach or one particular method, but there are a number of different things happening in parallel. One of the most important things is that Google, and I'm using Google as just one example. The story is very similar if you check the environmental report of Meta or other tech giants as well. So Google has signed a contract of 8 gigawatt purchasing clean energy, generating and purchasing clean energy. And it claims that 2.5 gigawatt was online in 2024 alone. But that is the improvement that comes from the clean energy, which you see in this figure below, where you see that this gray part, which is still the energy that is consumed, but it's much less, and it's clean energy that is consumed. And there are innovations across hardware, software, which means for the same amount of energy that whatever amount of work you could have produced 5 years back, now it's 5 times, 6 times more. So developments are happening in all fronts in parallel, and that's something good to be hopeful to the future. In this figure, we see that the PUE uses efficiency that is now This is from 2024, but it's close to 1.08, which is not one, but it's quite close. So that's good. That was a little bit about data centers and computing mainly, although today I will be focusing on a more high level energy systems context than exactly computation and caching. But when we talk about networks part, then it's not only computation, but also communication, especially the wireless, the transmission part here, as you see, which is responsible for the highest amount of energy consumption. And also caching, storage, and especially when it is in the wireless network, they also consume a large part of energy. So it is very important to look at these different aspects together: communication, computing, and storage, caching, sorry, all together. So what I will do next is I will present very, very briefly 2 slides about our work on networks, focusing on energy efficiency. And I was a bit unsure whether or not to include these slides since my plan is to talk about this cross-disciplinary project today, but I couldn't help myself. When you get an opportunity to present, that we are all like, you want to present everything you can. So I shortened and put it into 2 slides, but this one is were from 2018, where we introduced a 3-layer integration architecture, and end user, edge, and cloud for mobile edge computing for energy, for enhancing the energy efficiency of IoT devices. Basically, the green, that's why we call it Green Internet of Things. And now this architecture and this idea of 3-tier network for energy efficiency, this has become quite a classic paper, and this idea is used in many, many papers. But at that time, it was quite new. And here you see that instead of doing processing everything locally, which is this green line over here, or doing offloading everything to the edge servers or to the cloud for computation, if you do selective offloading, which means certain tasks on the devices and certain tasks in the edge to the edge and the cloud, which are connected, then you can actually receive much lower energy consumption per device and also meet the latency requirements as specified. This is another paper from 2020, 5 years back, where we do joint modeling of computation and resource allocation for 5G beyond, where you see that this one over here is the total offloading to the cloud, and this one is local computing, this full offloading local computing, and this one is the proposed GDPG-based algorithm for selective offloading and joint resource management. So what this basically shows is that all of them scale more or less linearly as the number of devices increases, which is natural. But despite that, this one, when you do joint resource management and selective computation offloading together, this one performs much better. But probably that's not very insightful. What is more insightful here is in the second figure, figure 4, where you see that type 1 and type 2 are the kind of computation intensive tasks, and type 1 and type 3. And type 2 is, it's not computation intensive, but it's a quite large chunk of data that you need to transmit if you really need to offload it. So what we see in this figure here is that for type 1 and type 3, this is energy consumption of each device. So this is local computing, the blue ones, the brown ones are full offloading. If you do if you make use of the proposed algorithm, the enhancement in terms of energy consumption per device is very high, quite significant. This one over here is the total system level energy consumption. This one is per device. But in the case of type 2, which means the data size is large, but it's not really computation intensive. In that case, it is better to actually do local processing, which consumes the least amount of energy. And that's basically because you spend a lot more energy in transmitting the whole data to the edge or to the cloud, and the actual amount of energy for computation is not much. But in reality, the traffic is usually mixed. So our hypothesis in this paper is that you for real traffic, which is usually a mix, the Bose algorithm still is the best or outperforms the total offloading or the local computing based methods. Okay. Now zooming out from that, which are the two slides that I couldn't resist putting in, although I will not be focusing on that today. So zooming out, if you look at the global energy consumptions here from 2022 onwards, there is increase in energy consumption, which is natural. And from after 2023, the increase at that time was projected to be quite high to drastically increase, basically. And if you look at the carbon emissions here, it's more or less, this is 23, and after 23, it's a projections. So it's going down slightly, at least, in all parts of the world, except in some parts, India and the Southeast Asia, where the population and then the access and use of technology is increasing rapidly. So if you look at the worldview here from 2023 onwards, it's more or less, how do we call this? It saturates or with a slightly downward trend, which is, again, not very close to the goals, but it's a positive sign. Okay, now with this, why do we shift this slightly more or less saturation or slightly downward trend? A lot of that has to do with it is not clearly not the reduction in energy consumption. The energy consumption has been increasing simply because the population is increasing in many parts of the world. Technology, the applications, different domains. It's really going upward with a very high slope. But of course, the use of clean energy, generation, purchase, and distributed generation in different parts of the grid, not just offshore and onshore, but also with the users on their rooftops, community level power production, that is increasing. And there is clearly this paradigm shift happening from a centralized to a decentralized energy system overall, not just for computation and not just for networks, but for energy consumption as a whole. So this is the power grid more or less today. Maybe we are a little bit over here in somewhere in this arrow where we are moving to a microgrid based architecture where you see there is distributed generation at different levels and there are more interactions. We are not exactly here yet, but somewhere in the transition. And in the future, we would like it to be, at least the vision is that the whole power system will be a network of microgrids that are connected to each other, but that can also operate on their own, disconnect and operate on their own when as necessary, seamlessly. So the role of the energy edge here is important when we talk about the participatory approach. Whenever I talk about this kind of participatory approach and say what is an energy edge, and a lot of people, the first thing that comes to many people's mind is that, okay, you have solar panels on your rooftops, so you are a very active presumer or an important, that's how you can become an important stakeholder. And that's actually true, that's the starting point. But the concept of energy edge and the participatory approach is not limited just to utilizing your roof. It starts from there. But the idea is to bring consumption and production close to each other, and also to take to facilitate decentralized energy production and massive uptake of that energy from the edge, from the presumers and the edge all the way to the grid, which means it might be some other edge or it might be within the grid. So it depends the actual consumption, where exactly that power go. That depends on the structure and the algorithm, but it could be a virtual power plant, or it could be a transactive energy system, a peer-to-peer structure, whatever that is. But the idea is not just to generate power at the edge, but also to take that power upward. And then optimally exploiting this flexibility from the edge, while also mitigating the impact of uncertainty with now higher, more power production, renewable power production, which is quite a challenge. It has been a challenge from many, many years, but when you have distributed generation at different levels at the users, at the edge, at distribution grid, and there is so much uncertainty associated that remains. Although you have powerful algorithms now, but you cannot really predict 100% correctly. So exploiting the flexibility optimally while also mitigating this increased uncertainty, and then the stochastic presumer behavior and so on. Okay, so the whole idea here is distributed generation to unlock domestic decarbonization while also maximizing flexibility. Those are some keywords here, but the ultimate goal is enabling net zero infrastructure with enhanced user responsiveness, making the users a more important participant, stakeholder in the whole system, and also grid automation, that is the digitalization part, but all of this towards a more sustainable energy transition. So this is the conventional view of the smart grid, so to say, with 3Ds, decarbonization, decentralization, and digitalization. But we have another D here called democratization, energy democratization. And it does sound quite fascinating that we have all 4Ds, but it is equally challenging to model this kind of system and to bring it into practice. You need holistic modeling framework, integration of dimensions other than just technical, energy and ICT, societal dimensions, legislative policy making. And for that, you need cross-disciplinary approaches. Yes, I can move on. How am I doing? Okay, 19 minutes. Now, two papers again, very briefly. These are our works, but not exactly the publication after the project, just before that. But here we try to show that we're working towards modeling the prosumers, the users, and the parameters associated with them. So in this particular paper, we model the interactions between different households for intelligent load scheduling in residential smart grids. And we model the interactions as a non-cooperative game here. And there are two kinds of stochasticities that we do jointly incorporate: the stochasticity in the electricity price, but also the stochasticity in prosumer behavior in terms of their appliance, how they operate their appliances. So long story short, the algorithm that this is basically a non-cooperative game where none of the households want to share their consumption schedules with other households or even with the aggregator. But there is a little trick here where we have all that. That means they basically train their own models, but they just share the weight parameters, which is quite standard practice in literature now. But the little trick here is that the actor network is across all households. Each of them have their own actor network, but the critic network is common in the aggregator. So with this, you see that this blue curve over here, even though it doesn't start that well, but eventually it can give you the same performance as a centralized DDPG, which basically means as if the aggregator was solving the whole non-cooperative game equilibrium. Another one very quickly. This is also from a couple of years back, 3-4 years back, intelligent charging management for electric mobility, where we model the interactions between the power grid and a charging station with renewable power generation, while also incorporating the preferences of the users. Preference in the sense queuing time, charging time, and so on. So what you see here is the blue one is our method. The rest, the red one is offline charging cost optimization method, and the others, green one is when you have information about forecasted power generation, renewable power generation, but no information about forecasted price. The yellow or the brown one is information about both forecasted price and forecasted power generation. So here you see that our method can achieve more or less a comparable performance in terms of charging cost to the offline charging algorithm, but not exactly as less. The offline one performs much better, which might be a little bit counterintuitive. The reason is that if you look at the curve, the plot here, QoS plot, here you see that while the cost is the least in the offline algorithm, but in this case, so is the QoS. And with this blue one, the cost is comparable, slightly higher, but the QoS is much higher. So the idea of putting these two papers here is that user preferences, user dynamics, user stochasticities, those are brought into our studies even before we actually started working extensively on the project. So then we see that the participatory approach, actually, by now it is quite clear that the sustainable energy transition does need a participatory approach, and the end users or the energy edge needs to be an important stakeholder in it. And there are many pilots that are based on this kind of idea. Brooklyn Microgrid is one of the pioneering ones. In Norway, we have something similar, although smaller scale, called Valor Microgrid. There are many others. Transactive Energy Colombia, for example, Sulshare in Bangladesh, Piccolo, the online trading platform in Australia, and also a number of projects. All of these are from Norway, and except the top right one here, which is an EU project. But I'm sure there are many other similar incentives all across the world. So what's the point of highlighting this? Is that although there are so many initiatives, projects, pilots, test beds, but if we really look for the commercial scale, large scale deployment, we may not find many. What can be the reason for that? We believe that there has been enough research on energy systems optimization. It's not really a very, very new topic. And also energy informatics, energy informatics in the sense the ICT technologies for energy systems. But that alone, and the technology readiness level is quite high. And we all realize that participatory approaches are important, but at the same time, there are different dimensions other than technological, such as social psychological factors and the policy, the regulatory aspects that are very important and becoming increasingly important, but that are not necessarily given as much importance. Privacy lies at the intersection of both of these, according to us. So we have this project called Prithem, Privacy Preserving Transactive Energy Management, where we want to do research at the intersection of these to generate new knowledge and novel insights for sustainable energy system. It's quite a reasonably big project where we have two professors from psychology. I am leading the project, and we have some other professors also involved. And we have two professors from the Faculty of Law, all of them from University of Oslo, one on energy law, another one on data law, and we have also two professors from ITS, the Faculty of the Department of Technology Systems that mainly does research on energy technology. And we have industrial partners and also regulators. And one postdoctoral researcher, Shiliang here, who will present later, is also working in this project. And we have a number of PhD students in different departments. The project is, as I said, it focuses on a couple of different things across different departments, but here is the idea of the project in a nutshell, where the main focus is on prosumer empowerment through trust enhancement. Trust enhancement in the sense you try to build the trust of the prosumers in actively participating in something like transactive energy systems, either peer-to-peer or peer-to-grid, where and you try to measure their intention to participate actively towards this participatory approach. That's a non-technical part and a little bit abstract, but on the technical part, distributed machine learning, data analytics and machine learning, and also secure data sharing. And then we have work packages on social psychological perspective, which is led by the Department of Psychology, one PhD student working on that. Similarly, regulatory and legislative considerations. The final work package is, of course, the energy system optimization, which is partly similar to the conventional optimization, but now integrating all of these different dimensions. Now, this is a short paper from last year, my PhD student, the first author, Huizan. This is a very simple paper where we do introduce the concept of personalized privacy preserving personalized pricing scheme for the smart grid. The idea is we often believe and use the kind of models where we say, okay, privacy is either very important and all the users all the nodes are either implementing some kind of privacy preserving mechanism, usually federated learning plus some noise, differential privacy, uh, or or they trust on some third party. So that is the usual kind of setting. But here in this paper, a short paper, the users have a say about their privacy preservation coefficient, or willingness to share the level of you add some noise in the weight parameters that you share with the aggregator, but you are willing to customize that, and that is your personal privacy coefficient, so to say. The agreement here, which is how it usually works, is that all the users, the households, they train their own models and then they share the coefficients with some noise. But then they have an agreement with the aggregator that the amount of discount in the electricity bills is proportional to how good data or the parameters they share. And that is where their personalized model comes in. So it's a very short paper. The Hui is now working in actually an extended version of the journal paper, which is not included here. But if you have interest, I think I can, yeah, we can discuss about that. This is another work of, this is from the Department of Psychology, Juliana. She's a PhD student there. And she has conducted two and a half surveys, I say usually, because two of them were successful and the one was not very successful. So this was her first study where she conducted a survey about the potential intention of people to participate in a technology like peer-to-peer transactive energy systems. The thing is that, again, conducting this kind of survey and trying to understand people's intention, that's again not a completely new idea and not the most innovative part. I think you can find a lot of such surveys back from 2005, 10, and so on. But most of them were about using renewable energy, clean energy, maybe paying extra for that. But that was not exactly in some sense participatory, but not exactly actively participating and producing and selling your electricity back to the grid or to your neighbor or to some another peer. So many findings from the surveys that were about adoption of DERs, distributed energy resources, they are relevant actually, but not exactly transferable when we are talking about peer-to-peer or any form of transactive energy systems. So this kind of survey is quite interesting and insightful. And this was also a short paper. The key findings from that paper were that there are three things that are important that can influence the intention of people to participate in such surveys: attitude, perceived behavioral control, and subjective norms. So in attitude, there were a number of different criteria within attitude. I do not remember all of them now, but at least what we found as important are the sense of novelty, that you are doing something new that really excites people, and that positively influences their intention to participate. Perceived value added to existing investment, not something completely new perhaps, but if they can reuse what's there and if they don't have to completely throw or lose on their existing investments. So they significantly explain variance in intention of different user groups. Among subjective norms, perceived support from the local community seem to be important, and surprisingly, which basically means the subsidies from the government or at the community level. Surprisingly, subject matter experts, they seem to play a significant role, it seems, which means many people don't understand. These are technical stuff, and even though it's not much they have to do, but still people do not really understand a lot about what is peer-to-peer energy trading, or what is energy trading and what is transactive energy system and so on. So if a subject matter expert really goes and talks to them and explains things, that is quite able to change their intention to some extent, so to say. And about perceived behavioral control, the intention to participate is also influenced by the perceived ease of integration. That's probably closely related to perceived value added to existing investment, but also the technical part where they don't have to really, it shouldn't be something that the users need to do a lot and play with a lot, but it should be something more or less automated. Juliana, she also conducted another study very recently. Okay, wait 2 minutes. Great. So this is a more detailed study, and she has submitted a journal paper. The paper is still under review, so I did not get permission to say much about it, to include the paper references. But yes, this was a much larger survey where the actual sample space was bigger, but I think 456 valid subjects. And it was completed very recently, November 2024. But the paper was in writing from already before, and then they added some results here. The main contribution in this paper, it sort of builds up on the previous paper, but it's a new paper altogether where where Juliana introduces this two-tier integrated framework that demonstrates how bandwidth and fidelity dilemma can be solved, which basically means the broader contextual factors, the influence of the contextual factors, and also the deeper factors, individual user-specific factors in the intention to participate. And also another, not finding, but validation is that the perception of loss indeed looms larger than the perception of perceived gain. And also the effect of experience on perceived social and situational confidence can be more profound than its effect on perceived utility and ease of use. So these are these are not the words that I am used to myself, but this basically means that your intention is not necessarily dependent only on how much you are going to get or how much you are going to lose, but it has a deeper root in your value system, your belief, and so on, and how you are influenced by the social circle and so on. Okay, key findings from this paper, which is still under review. Biospheric and egoistic values positively influence participation intention, which means biospheric is basically environmental concerns, and egoistic means your own sense of novelty, satisfaction by making use of a new technology or by being an active participant in it. Experience with similar trading technologies directly and indirectly enhance the intention to participate in peer-to-peer energy trading platforms. Anticipated hedonic motivation and perceived price value are very strong indicators of potential intention, which basically means hedonic motivation is your sense of gain and loss. If you calculate it with some metrics, maybe it is different, or the how many times. For example, I talked about just one slide back that people usually are more concerned about the loss, 1.75 times more concerned than the same level of gain. So whatever gain you can get, you usually, if you evaluate 1 times 100%, then if you lose the same amount, if there is a potential to lose the same amount, you value it 175%. So this is your perceived notion of gain and loss, and how that affects your motivation. That is hedonic motivation. So hedonic motivation and perceived price value play an important role. And more importantly, this hedonic motivation is guided by your own beliefs, values, which is again influenced by the social circle and many other factors. So there are very specific terms from social sciences, psychology, which I am not very familiar with, perhaps, but this is my understanding. And actually, I am not a co-author of these papers, but these two papers are also the publications from the project. But I, as a coordinator, as the project leader, I know what kind of surveys they've been doing, and we discuss the results and everything. But these are the two papers from psychology department. Okay, now, yes, this is a review paper, a little more than a review paper actually, and this is another joint paper where Shi Liang is my postdoctoral researcher, the first author. But this is a joint work with Lee Andrew, who is a professor in the Faculty of Law, and he is an expert in data law and the head of CERI, the Center of Data Law at UIO at the Faculty of Law. So this is a joint work, a cross-disciplinary one, I think we can call it. So what we do in this paper is, this is also currently under review, but it is available on arXiv. And what we do here is we review the EU legislative frameworks on for the energy sector, mainly focusing on data-related issues. And we do categorize everything into three main pillars as data sharing, cybersecurity, and privacy. I think cybersecurity and privacy protection are probably not that surprising. We all do expect that, I think, but probably data sharing there is a bit of a story behind, but we can take that in the discussion. As I see, I am a little bit behind the schedule. All right, we do a lot of different things. It's a very long paper, but just a few things to highlight here. What we do here is for these three main topics, data sharing and privacy protection and cybersecurity, we do review all the EU regulations from 2006 all the way until 2024, just before we submitted this paper back in March this year. And then describe, compare, relate all the regulations that have come along, but even more than regulations, different kinds of efforts, work groups, documentations, concrete documents or ad hoc documents that came along the way, and also show how each document is connected to every other activity in this direction. Also, privacy protection, that is much more detailed, where you have this phase from 2006 to 2010. We call it pre-privacy sort of, and then 2010 to 12, and then 12 to 16, and 16 all the way until 2024. The same for cybersecurity, and I'm sorry about the size of the text here. Maybe it's not big enough, but in the paper, I think you can. It's not that big in the paper either, but I think there are more details there. Again, it's a long paper, but I wanted to use 2 minutes to talk about this part, the reflections on the evolution of the regulation in the energy sector. What are our reflections, and especially the gaps, and what we would like to see more. So first and foremost, the contextualization with respect to the energy sector, where we basically compare the three aspects here, as in what kind of activities have been happening, we have seen, and which one has sort of received more attention. And we see that data sharing is the one that has received least attention. Maybe it is also understandable because security and privacy protection are perhaps more concrete than data sharing. But the reason we had this also as a separate pillar is because when we reviewed a lot of works, we had more than 300 references that we reviewed for this paper. And there were many papers that do not talk explicitly about security or privacy, but about data sharing. So it was essential for us to also have this as one dimension, but it has not received as much attention as either cybersecurity and privacy. And surprisingly, or maybe not, privacy protection is the one that has received the most attention, with work groups and the change in the regulation landscape happening very fast with GDPR and all the EU AI Act, Data Act, everything. This is the one that is evolving very rapidly and getting the highest level of attention, so to say. We also identified some scenarios that have high technology readiness level, but have not received enough, but there are no specific regulations or standards, such as in the case of independent aggregators, their role in the market, vehicle to grid scenarios, and so on. Okay, I'm probably a little bit over the time. Another one, also very important, in the paper we discussed the architectures and the structure for enforcing the privacy protection, security, and cybersecurity in Europe, at the European level, and then at the country level, and so on. And for that, the role and the responsibilities of different stakeholders, active stakeholders, is very, very important. But in this case, it is a bit, in many cases, it is not clear. For example, if it's a DSO, what exactly are the rules and regulations for one specific application, but for another application, those can change. But the DSO has multiple roles in different scenarios, and then it is not always clear which role exactly it should take. So it is important to conduct a role-oriented regulatory analysis to derive explicit guidelines for specific targeted energy stakeholders. Another one is about the EU AI Act. Okay, so yes, most of the discussion in the AI Act is about the risk identification and anti-risk systems, and we feel that it's a bit heavily focused on the high risk zone or high risk applications, which makes sense for healthcare, for example, where almost everything is personalized and sensitive data. In the case of energy, it's not exactly the same. There is non-personal data, there is personal data, but personal but not sensitive, and personal but sensitive data. There's also data that is sensitive and high risk, perhaps, but not personal. So these kind of differentiations, these kind of distinctions are probably not exactly as concrete as we believe it should have been. So that's that. I probably took two or three more minutes. Sorry about that, but I would like to now hand over the table to my to Shiliang, and I'll come back with the last slide after Shiliang. Shiliang, please.
Yeah, so I share my screen or use this one?
Yeah, we can go. I can
Okay, thank you.
press next for you. Yes.
My name is Shiliang, and I present my recent work on energy and open data. Particularly, I will present a data we created for the electricity and the power system in Norway, and I also show a use case. Next, please. Yeah. So we call this work Norwegian electricity in geographic datasets. So we target a dataset that can represent the electricity in Norway. For example, power infrastructure, energy consumption and production, etc., and how they distribute in the entire country. We start with looking into different data sources from open resources like OpenStreetMap and governmental agencies and also third parties. Yes, so we look at the resources, and some of the sources are in good format with good data, but some data are in irregular format. So what we do is that we go through software work to process the data, so that we clean, filter, and reformat the data using different formats, so that the final product is that we get either CSV file or GeoJSON files for the dataset with the most relevant features. We released openly on the Nodal, and beyond that, we also release our code openly. And we also visualize our datasets in interactive maps so that users can get an intuitive understanding of our data. Next, please. Yes, so the dataset we release is directly downloadable from the Nodal, and we released it in September this year, and now it has accumulated like more than 300 downloads. Yes, next. Next. Yes, so our dataset includes the information like power grids, the main transmission and distribution power grids in Norway, and transformers and substations, and also hydropower plants and the regulated lakes that are relevant with hydropower production in Norway, and also wind power and wind turbine location, solar power and solar power generation estimated for each municipality in Norway, and also power consumption for each municipality in Norway. So with this dataset, it is possible to, for example, to simulate and optimize the power flow, to analyze whether there is any bottlenecks in the power grids, etc. Yes, next. Yes. So next. Yeah, so we have the energy data, for example, power lines. And from open sources, we can also have more data like road network, building prints, elevation, and building heights. So with all this data set, it is possible to create a 3D visualization that incorporates all of these elements. Next. Yes, so this is the result of a 3D visualization for the area of Arna, Oslo, in Norway. So we have the white lines and the roads. We have the red lines and the park grids, and also we have the light blue blocks as the buildings in this area. Yes, next. And but we go beyond the area of Oslo. We develop a API that we can use it to generate the visualization for any place in the world. And we call this API Synergy 3, which is short for City Energy 3D Modeling. So in this slide, I show two examples, one from an island in Scotland and another in a city in America. Yes, next, please. Yeah, so our API provides interoperability across different platforms, for example, Python, MATLAB, and Java. And beyond that, next. Yeah, we also provide previous one. Yeah, we also provide a web page that anyone can use our API without installing any software. So if we click this, next, please. Yeah, next. No, don't click, just next. Yeah. Yeah. So if you click the website link and then you found this web page. So what you can do is that next you click next, next. Yes. So sorry, previous one. Yeah. So you can fill in an API key which is free, and then you can fill in the place that you are interested. For example, montage in this example. Then you click the request button and wait for the response. Yes, next. Yes, then you will get the 3D visualization like that. So this is the area of montage in Montreal. So maybe you can find the buildings that belongs to McGill University. Yes, next. Yeah, so we saw terrain, roads, buildings, but there's no power grids in this visualization. This is because power grid topology is not always available from open data resources for any detailed areas. So to address this issue, our next step is to add power grid recovery from open data so that we can make this API a full-fledged one. Yes, that's all. Thank you.
Okay. Yes, this I thought I would keep it as my last slide, but I think in the interest of time, I would like to receive questions and discuss, so we can come back to this later on if there are questions about this. But thank you very much for listening to us, and we would like to take your questions. Thank you.
Thank you so much for the talk. So I see there's a question on the chat. Syed, you can unmute yourself and ask the question if you'd like.
Yes, hi. Thank you so much for a great talk. A minor question, actually, my side actually, is your data sharing different from Gaia-X system? Actually, Gaia-X from EU, as we already were, the data ecosystem related to data sharing in between Schengen area, actually.
Sorry, I didn't get your question. One more time, please.
Actually, I mean, the question is your data sharing different data sharing system? Actually, you already mentioned in your paper. Is it different from the Gaia-X ecosystem? So we already have actually a Gaia-X system in EU and in Schengen area in order to share data actually in between countries, actually Schengen countries.
Yes. What we can, okay. So the three categories that we have here, data sharing, cybersecurity, and privacy. This is, we did a kind of scientific literature survey for how many years, Shilian? How many years of papers is it? Is it from
It is
2000?
from 2024, sorry, 2004.
2006 to
That's right.
2024, I think,
Okay.
right?
Yes.
Yes, yes. So I think it is partly that, but also maybe beyond, where we talk about data sharing, which is not data sharing issues, which is not exactly bound to a specific type of sharing platform or sharing technique, but it is more general, which is mainly from the scientific papers that are from way before, from 2006. If that is what you...
Yes.
Yes?
Yeah. Thank you so much.
Yeah, so it's not limited only. Yes.
Thanks.
Yes. I think there are more questions.
Yes, so I see Stella, you have your hand up.
Yes.
Yes. Can you hear me?
Yes.
Okay. Thank you for the talk. So my question was about the privacy and the security part. Like, how do you address this two part of the problem? Like, is it at the system level or like in the project? How do you address privacy and security? Do you develop new systems or?
Okay. Yeah, that's a very interesting question. Okay, I will first answer for this paper, and then I will talk about the project. They are probably related, but do different things as well. So in this paper, what we do is we are not developing a new security architecture or protocol or a security mechanism. This is a cross-disciplinary paper where we collaborate with the researchers from the Faculty of Law, who is an expert on who also has a computer science background, of course, but an expert on data law and data regulation. So what we do here is we do review, but that does not mean that this is only about regulation. It's a bit tricky, but we, of course, so we struggled quite a bit how exactly you put together everything, and that's a very typical, very that's a classical challenge whenever you have this kind of cross-disciplinary collaboration or cross-disciplinary projects. Although it's very interesting, but it's also quite challenging. So we did review many papers, many of them technical papers. First of all, so I did not include a lot of slides here, but okay, maybe I should just. I don't know what happened now, but this one, for example, this is an example where we have like a typical survey paper or review paper. We did review several papers, technical papers, and then put them into different criteria, different categories, the three of them, but also with other aspects, like what kind of problems they solved, what kind of AI algorithms they used, what aspect of security was addressed in this particular paper, but did it also talk about privacy? So in many papers they were interrelated, many papers they were different, but they were all scientific papers. But in parallel, we also reviewed all the regulations. So in this case, all the regulations that are related to all three of them, one of them or two of them, or all three of them. Okay, so then we try to do a mapping of where does this paper fall, or where do these papers fall, and how are they related, and so on. But the eventual contribution is, I think there are a lot of papers that do review papers on security and privacy. We probably don't need another one as such. But the main contribution here is this mapping between where this landscape of privacy, security, data-related issues, so to say, is going, and how is the regulatory landscape developing, and how do you see the connections between these two dimensions, and what are still the gaps the way we see it. And so that is the main contribution. We are not trying to develop any, I mean, we are actually in some other papers, but in this particular paper, the focus is two parallel dimensions: regulatory, technical, and interconnecting them. Yes. In the project, we do talk about privacy preservation, as in we do not really want to develop something very, very complex and very complex and something that no one else has done. But our main focus is on developing solutions that are easy. And we put a special focus on low complexity and low cost. That is one of the main focus areas in the project. Now, this is different from this paper. Where in the project we have students who are working at the Department of Informatics. I have 2 PhD students, and Shiliang is a postdoctoral researcher working at the Department of Informatics, where we focus on the technical issues. But having said that, this is a cross-disciplinary project. So we try to bring in aspects from other departments, other disciplines as well. I can give you an example. My student Hui, I presented a paper here from her, a short paper. That was this one. For example, she's working on personalized privacy-preserving, personalized pricing scheme for the smart grid, where most of her work is on the technical part, at least in this paper. But now she's working on a journal version where she is using, she has different kinds of uses, privacy-oriented, economy-oriented. That means they are more concerned about the reduction in the electricity bills than maybe privacy. It's not 0 and 1, but you have privacy oriented, economy oriented, balance oriented, and also she's trying to use some surveys from Juliana's, some findings from Juliana's survey, where they find what and how do people value these different aspects. So is it in reality in certain regions, is it people who are more concerned about privacy or about economy, or is it more of a balanced population? So, and then she uses something called a prospect theory and from psychology. So that will be a very cross-disciplinary work, although the technical part is still on privacy. Yes.
Okay, thank you.
So maybe I'll also read Bettina's question in the chat. She had to drop to go to a different meeting. So
yeah, sure.
She is asking about the slides with the 4 Ds. So she's wondering whether the goal of the reduction can also be incorporated into an approach that tries to address all these objectives in a holistic manner. So far, we are in a phase of ever-increasing demand in compute, and the question is whether one can aim in requiring less compute.
Okay, now I can see the question. Let me read through. That was quite a long question. Give me 15 seconds.
Sure.
Okay. Yes, 4Ds. Goal of reduction can also be considered incorporated into an approach that tries to address all these objectives in a holistic manner. So far, we are in a phase of ever-increasing demand on. And the question is whether one can aim in requiring less compute. Yeah, I think this is again a very big question, but also an open question, I would say. I will anyway go back here, although I'm not sure how much that will help. But yes, yeah, I think it is necessary actually to do this. This is something that I also have thought quite a bit about, and we discuss very often, but usually we don't come up with an answer. That this is how it should be. Maybe I think in terms of yes and no, I think it's a yes. We should move more towards reduction than just, okay, it has been increased. It would be nice to also reduce the demands, especially since we are talking about sustainability, right? Sustainability is not just about increasing and some increasing consumption, but optimize. It is in a way, but it would be nice to also reduce the consumptions across all different dimensions. And here it's also very interesting. We talk about digitalization here to make the energy system more, to enhance the energy system, to improve the performance of some sort. But at the same time, the digitalization part, especially now, the AI part is such an energy consuming appliance, so to say, right? Component in itself. So I think it is very important to consider reducing the consumption in total and not just to optimize and then to do intelligent scheduling and all kinds of intelligent algorithms. It is for sure, yes. But How is that possible? What kind of what kind of holistic modeling framework and what kind of objective that would be where we can reduce everything? That is, I think, still an open question. That will remain an open question, I think. But if we really talk about sustainability, it is a yes. And there are also some positive efforts, for example, towards that direction in terms of reducing and not just making it more intelligent and more um, we often say, even when we look at those environmental reports, either from Google or Meta, they say that okay, the carbon emissions are reducing despite increasing demands, but the consumption is actually increasing, right? And when you say we do not count, it's a bit of it's beyond technical actually. So you do calculate, and then you do say, I also had that one slide where you say it reduced by 12%, and then the compute power for the same unit of energy has increased, and so on. But actually, you are consuming more energy, even though that is green. But it does take resources also to produce that green power, right? It doesn't come just from the middle of nowhere. And then there are a lot of discussions about how that power is created or generated, and then the hardware required for it, and then the environmental concerns of, for example, solar panels, turbines. So it goes a long way, but that's, I think, a bigger discussion. And in parallel, there is this circular economy, circular technology research happening, where you try to, even, for example, even if we don't talk about the very big things, the electric vehicles, electric mobility, that became very popular, and many of you probably know that Norway is the EV capital of the world. So the penetration of EVs here is very, very high. But then what happens after 5 years, 6 years, when the performance of the batteries declines, and then you want to buy a new battery, or you just want to buy a new car because of the difference in price is probably not that high, or even it's more rewarding to buy a new car, and so on. So these are discussions, broader and bigger discussions, but it is important for sure. But how exactly are we going to do that? That's I think that needs more work. Yeah, so to say.
Thank you. Are there any more questions from the audience? I see nothing on the chat. Also, in the interest of time, maybe I will end with one question that's for Shiliang's research. So I'm very excited about the data set that you propose. I'm just curious if you can give a bit more details in terms of what this looks like and how big it is. So in terms of gigabytes, can you give please an estimate on how much data you have? And in terms of formatting, is it like a time series, or how exactly would one access this data?
Yeah, thank you for the question. So it's in gigabyte, and it has several files. I think, if I remember clearly, I think more than 10 is 13 files. And I have several in both. I think I have 2 or 3 files in both CSV file and GeoJSON files, and the remaining ones are all GeoJSON files. And about the format, about what the time series. So we have both time series and also some other data set that is in the format of GeoJSON file, which is a commonly used format for GIS systems, for example, QGIS or ArcGIS. So that in such GeoJSON file, we have the location and also quite more other features in the data. I'll give you an example. For example, we have the power plant data in GeoJSON files. So we have the location, that is the longitude and latitude of the power plant. And also we have the type of this power plant, whether it's a hydro or solar power or wind power. And we also have the capacity for that power plant. And this is a typical GeoJSON file. But we also have time series like the energy consumption for each municipality in Norway in a monthly basis. So we have both.
That's awesome. Thank you. Thank you. I'm looking forward to checking it out.
Thank you.
Okay, so we are a little bit over time, but I would like to end this by thanking you both for a very interesting presentation. So we learned a lot, and if there are other questions, I encourage our students to let us know, and maybe
Please
we
feel
can
free.
forward the questions to you.
Yeah, please feel free to reach us. I think you can easily find our email addresses. Well, thank you very much for the opportunity. It was great interacting with you all. Thank you.
Thank
Thank
you.
you very much.
So